drawing field lines and calculating net electric field for individual charges is all well and good, but we can't really do anything with a single proton. What we'd like to be able to do is to force electrons around things, to accelerate them to high speeds, give them some kinetic energy, and then use our assorted electronic devices to capture those electrons and absorb that kinetic energy and use it for something handy, like lighting a light bulb or making a TikTok video, if that's a worthwhile pursuit. Anyway, so what you've got in a power plant is a bunch of electrons being moved around, and so you get them going and you charge them up with energy, and then you send them out to devices, and the devices pick up that energy and use it. So that's the idea behind electricity. So we need to be able to get those electrons moving, and we need to be able to do it on like a human-sized scale. I think we were discussing earlier the idea of the vacuum tube television, the cathode ray tube, CRT monitors, etc., and how they had an electron gun in them. And like the way that machine worked is it fired the individual electrons to scan across the screen, lighting up individual pixels in order to make them glow so that you would see a picture on the screen. So being able to target electrons with that degree of precision, right, to be able to target a dot that is so small that your eyes can't see it as a dot until you're within 5 or 10 centimeters of the screen. And within that dot, it has a red, a green, and a blue pixel that electron gun can zap one or the other in order to make it glow in the appropriate color. And do that, scan the whole screen, millions of pixels, millions of choices between those 3 colored spots, and it has to do it at least 60 times a second, or else you don't see a moving picture, you see a series of still images. That level of control over a teeny tiny particle that is so small, right? Like the mass of an electron is 10 to the negative 31. So comparatively, the mass of an electron compared to a kilogram is approximately the same as the mass of 1 kilogram compared to the mass of our star. So it's very small. So how do you get something like that moving around when it's so small that you can't even conceive of how small it is? Well, there's 2 things you've got to be able to do. You've got to get them going, and then you've got to be able to steer them. So the parallel plates thing is how you get them moving in the first place. So if I could draw something for you, I'm gonna give you a little proton here, and I'm gonna give you a negative charge. And the way field lines work is they come out of positives and into negatives. So there'll be one like this, like so, and there'll be one like so, and then so on and so forth. Now, if you can remember that these field lines are supposed to be acceleration paths. So if I were to put a test charge, if I put a proton right there, the idea of the field line is that the repulsion of this proton and the attraction of that electron should make this thing accelerate along that path. Now, because of that, these paths can't cross each other. You can't have a pathway that does this. And just for a simple logical reason, if I were a proton on that path and I got to here, I would have to choose which path to follow. And protons don't get to make choices. Their pathway is predetermined by the field layout. You can't have these particles stopping at an intersection, scratching their heads, and deciding which way they want to turn. That would certainly make for a more interesting universe. It would also raise all sorts of interesting philosophical questions like, what do protons dream about? And you don't want to go there. I'm sure they're ugly. Anyway, what's the point? Field lines can't cross each other, so let's get rid of that one. Okay. So you've probably seen a diagram like this in the grade 11 course, or if you shook iron filings near a magnet, you would have seen this sort of path structure appear. What we're going to do here is we're going to introduce another proton and electron charge reasonably close to these two, like that. So if I were to draw the pathways around this, and there's an easy one there, and there's an easy one there, but I can't draw anymore this way, because I would have to cross the field lines generated from the original pair. So that's a problem. So I'm going to have to draw my next field line. Maybe get one there, maybe one like that. If I draw the next one out here, I'm going to have to cross this pathway, which means that this field can't show up. Why am I erasing this one and not that one? Well, this one is closer to this edge, so it's going to dominate. Get rid of that. So I get something happening like this. Okay, lovely. I'm going to do it again. I'm going to add in another pair, just about here. So I get field lines like this, and some like this, and then this field can't manifest anymore, because I have to be able to draw these ones around here, like so. Okay. Now, I've only drawn 3 charges, or 3 pairs of charges, 3 on this side, 3 on that side. And already there's a bit of a pattern happening. In this particular region, right up here, there's all sorts of swirly, crazy patterns. And down here, there's all sorts of swirly, crazy patterns. But in this region right here, if I erase everything else that's around it, I end up with this nice set of straight field lines. Okay, going from this side to that side. Now, if I were to take these charges, well, so anyway, why is that helpful? Well, because if I put electrons on this side, they're going to follow those field lines. And instead of going on these crazy swirly pathways, they're going to go directly that way. So if I'm trying to accelerate a charge, I don't want it accelerating necessarily on this curve. I would like it to go in a straight line. So if I set my charges up this way, lined up like so, I start to get field lines that are pointing in a straight direction. There's a little bit of curve here. So how do I solve that? Well, I'll just introduce an extra set of charges like so. And because my field lines can't cross each other, in this little region here where I have a high density of charges, my field starts to look like beautifully straight lines. Because the next one from this charge bumps up against the next one from this charge. Like so. So in here, I'm getting this nice field that's passing in that direction, and it's reasonably parallel. And I accomplished that by drawing 5 pairs of charges. So I'm going to give you a different diagram. I'm going to draw a steel plate. Well, it doesn't have to be steel, it's just a conducting plate. Maybe copper would be better. And I'm going to draw another plate like so. And I'm going to attach it to a 9-volt battery. Like so. Okay. So what's going to happen there? Well, if this thing is 3 or 4 centimeters long, I'm not going to end up with 5 protons on the top plate and 5 electrons on the bottom plate. I might end up with 5 moles of protons, 5 moles of electrons on there. That's probably too many, but you get the idea. It's more than 5 pairs. If I was already getting nice parallel field lines from only 5 pairs, if I put 10 to the 23 pairs on there, I'm going to get a nice parallel field inside that thing. So my positive terminal, and here I am crossing my fingers hoping I've labeled those properly. Positive terminal is going to end up creating net positive charges on this plate. Lots of them. Negative terminal will end up making lots of negative things on that plate. And in between those 2 plates, I will get a nice uniform parallel electric field. Like so. Now there's a bunch of math. Oh, I maybe finished. Now at the edges, I do get this curvy nonsense. Looks like ears. But in between them, they're nice and parallel. And there's a bunch of math you could do to try and prove this, but I would encourage you to just accept it as truth. That not only are they parallel lines, but it's also uniform strength. So it doesn't matter where you are inside of this electric sandwich, you're experiencing exactly the same field everywhere in this direction. And you can calculate the strength of that field based on 2 very simple characteristics of this setup. The field strength in between there, I'm going to use a big curly E for field strength, is simply the voltage you applied to those plates divided by how far apart those plates are from each other. So D is this distance, and V is this voltage over here. Okay, so in this particular setup, if I made these things like 2 micrometers apart, then the electric field inside of there would be 9 volts divided by 2 times 10 to the negative 6 meters, gives me 4.5 times 10 to the 6, I think. 9 divided by 2 times 10 to the negative 6. Yeah. Okay. Unit on that would be volts per meter. Okay, that'll do. All right, lovely. What I've built there is called a capacitor. You can find these in all sorts of machines. I found one in an electric dryer once. If you have an electric motor, they have a real hard time getting started. Once they're rolling, they're good to go. But getting enough punch to actually get the drum to start to spin takes a lot of energy. It takes a lot of current all at once. So if you can build yourself something like this, you pack a lot of energy into the electric field as you set it up. And then when you initialize your dryer, the circuitry doesn't matter, but you can absorb the energy that's captured in this electric field, and it gives it that punch at the beginning in order to get the thing spinning. If you've ever heard an electronic device, when you turn it on and there's that pitch, the low hum that becomes really high as you go, what you're actually hearing is the electric field manifesting itself in space. You can hear that electric field form. That's how much energy there is packed into these parallel plates at comically close distances. Okay, good. So now that I have an electric field that's established there, suppose I put in a little light bulb here, a little hot filament, What color should I draw that? Let's just do this as my electron source. Now, if I get a hot wire there, when the wire's hot, the electrons are easier to liberate. So when I introduce those easily liberated electrons into this massive electric field, it will rip them off the filament and fire them across my capacitor plates. So by doing that, I'm experiencing a force, and the force equation is the same as it was for point charges. Your force will be the charge on the object you introduce multiplied by the strength of the field. So if I introduced an electron at this place to this particular field, the charge on that electron is 1.6 times 10 to the negative 19 coulombs. And the field I'm experiencing is 4.5 times 10 to the 6 volts per meter. So if I work that out, the force should be that number times 1.6 times 10 to the negative 19. This would be 7.2 times negative 13 newtons. Newtons because it's a force. Now, do you notice that newtons, this unit came from coulombs multiplied by volts divided by meters? That's kind of curious. So I'm just going to make a note of that up here maybe. Newton is the same as a coulomb volt per meter. Those are weird units. But fine. So I have an electron experiencing a force. Well, if something with mass experiences a force, then it accelerates, right? That's one of Newton's laws. So force is mass times acceleration. So if this amount of force times 10 to the negative 13 was applied to an electron whose mass is 9.11 times 10 to the negative 31 kilograms, what would its acceleration be? I just have to divide this by this. And if you have any number sense with scientific notation, you are already chuckling to yourself. 1 times 10 to the negative 31 gives me 7.903 times 10 to the 17 meters per second. That is hysterical. That kind of force, right? Like that's ridiculous. In order to hit the speed of light, right? Speed is acceleration times time. At this acceleration, I would need 10 to the negative 9 seconds, so a nanosecond. Yep. In less than a nanosecond, this electron would have achieved the speed of light, which it can't inside the capacitor, because if you're accelerating at this kind of rate, it doesn't take you very long to cross a 2 micrometer wide capacitor. So why don't we answer those questions, right? It's just kinematics. So if I have an acceleration, if I assume it has an initial speed of 0 and I've calculated the acceleration at 7.903 times 10 to the 17 meters per second, then I should be able to get the final speed and the time it takes to cross the capacitor. Now those equations, or the kinematics equations, only apply for constant acceleration, which it turns out this little field setup will accomplish for you because the field is uniform. So no matter where the electron is, it is experiencing that amount of acceleration in that direction. So I'm just going to erase some of this stuff so that I can do some work. So there's a kinematics equation that's going to allow me to calculate the final speed if I have an initial speed of 0 an acceleration of 7.903 times 10 to the 17, and a distance of 2 times 10 to the negative 6. So in order to get that, I'm going to have to do this times this times this, and then square root. So that acceleration times 2 times 10 to the negative 6 is times 2 equals square root equals 2. Let's try again. 2 times 7.903 times 10 to the 17 times 2 times 10 to the negative 6 equals that to the exponent 12. All right. 1.778 times 10 to the 6 meters per second. Now that's less than 10 to the 8, which is encouraging. So I'm gonna divide this by 3 times 10 to the 8 just to get my percentage of the speed of light. Gives me too many things going on in my brain. 0.6% of C. So that is remarkable in 2 different ways. One, it's not even close to the speed of light, so I don't have to worry about relativity quite yet inside of my parallel plates here. But it's also almost 1% of the speed of light, which is way faster than anything else that's ever been tracked. So that's kind of neat that we can get particles moving at that kind of speed. And if you have that kind of speed, right, keep in mind kinetic energy is 1/2 mv squared. If you can get speed up there, then you get to square that speed. There's a lot of energy packed into those particles. So we're going to come back to that in a minute. Okay, so we just need some time then. How are we going to do that? Vf minus Vi equals At. So if I have a V final of 1.778 times 10 to the 6 minus an initial speed of 0 and an acceleration of 7.903 times 10 to the 17 times the time, I just have to take this number divided by that number will give me my time to cross the capacitor. So 1.778 times 10 to the 6 divided by 7.903 times 10 to the 17 gives me 2.25 times 10 to the negative 12 seconds. Is that a picosecond? I always get a little lost below -9. 10 to the -9 is nanoseconds, so this is 2/1000ths of a nanosecond in order to cross that particular plate. Okay, that's pretty quick. Some might call that instantaneous, but not quite. Okay, so I can get kinetic energy here, right? 1/2 the mass of the electron is 9.11 times 10 to the negative 31. And the final speed is 1.778 times 10 to the 6 squared. So the kinetic energy in this particular electron would be 0.5 times 9.11 times 10 to the negative 31 multiplied by 1.778 times 10 to the 6 squared gives me 1.440 times 10 to the negative 18 joules per electron. So if you could move a mole of electrons. So you're taking this, multiplying it by 10 to the 23. 10 to the 23 times 10 to the negative 18 is 10 to the 5. That's hundreds of thousands of joules per mole. So this little setup is very efficient at taking tiny particles and delivering enormous amounts of energy to them in order to get away with doing something. All right, good. Now, I had up here that newtons was a coulomb volt divided by a meter. So I'm going to hold this number here for a minute. We're just going to follow through with some algebra. If you recall, the electric field was the voltage divided by the distance, comma. The force was the charge multiplied by the electric field, which means that it's the charge multiplied by this thing, the voltage divided by the distance. Now, energy is supposed to be the force you experience multiplied by the distance over which you experience that force. So in this, then, it would be the force, Q, V over D, multiplied by distance. Now we have to convince ourselves this D down here was the separation of the plates. This D up here is the distance over which you experience that force, which happens to line up with the distance between these plates. So this distance and that distance divide each other out. I'm left with just the charge multiplied by the voltage. So if I were to try that, charge on an electron is 1.6 times 10 to the negative 19. I'm going to pop that in here. 1.6 times 10 to the negative 19. And the voltage I applied was 9 volts. So if I take 9 volts and I multiply it by that, I end up with 1.44 times 10 to the negative 18, which I already have. I already knew that. So that's nice that it kind of works out that way. So what this leads us to is that joules are maybe not the best unit for doing the energy contained in a particle underway, because we had to do a whole bunch of work in order to get joules out. But if I just do this, if I just have the energy picked up by a particle is its charge multiplied by the voltage that it is exposed to in a parallel plate setup, then I end up getting a number that is in electron volts. Right? That's the new unit. So just, we're not going to use it, right? Like you can just pop these numbers in and call that joules. But what I've got up here is that this thing is measuring electrons. This is measured in volts. So 1 joule is, well, that's backwards. A joule is equivalent to electron volts, and the conversion factor is the charge. That many joules is 1 electron multiplied by the voltage that you're exposed to. So if you see this up there, electron volts, that's an energy for a particle experiencing a static electric field, or parallel electric field, sorry. Okay, good. So I will set you off to the practice problems. They're reasonably straightforward. They're just using this little basket of equations in order to set up some parallel plates. So good luck.